think we should get started with the next session. So the next speaker, the only speaker of this session, is the only workshop organizer who has the privilege of giving a talk. Very competitive process. Yeah, so it's Michael Faulkner from Warwick. So.
Cheers, Sam. Thanks to the esteemed organisers for asking me to speak. We had a dropout, and then we thought that maybe a talk on statistical physics might be quite nice for the mixed-ish field. So I'm going to talk about something. So eventually, Monte Carlo, PDM, the PDM, essentially the PDMP used in statistical physics. Typically, we do what you could view as breaking symmetry on the auxiliary momentum space. And over the last I suppose 6 months or so, from discussing with Gareth, come to realise a little bit more about the significance of it, because in sampling algorithms like zigzag and bouncy particle sampling, my understanding is that when you get to higher dimensions, the dynamics become diffusive again on some timescale, Gareth. Yeah, I've understood that because Gareth's been talking about his non-reversible tempering techniques more recently. But when you break symmetry on momentum space, which is something you can, in statistical physics, which is something you can do thanks to the structure of the models, we seem to believe that you can maintain the ballistic style dynamics on longer timescales, and then this can accelerate sampling. So, quick intro. I know that not everyone in the audience is necessarily works on PDMPs or potentially in sampling algorithms, and many of you are not statistical physicists. So, quickly, eventually Monte Carlo is a piecewise deterministic Markovian sampling algorithm developed over the last 15 years in statistical physics. Werner gave a very nice talk about them yesterday, and then obviously there are many other, two in particular, famous PDMPs that have been developed in Bayesian computation in parallel over this time period. These piecewise deterministic Markov processes tend to accelerate mixing by driving through the state space with auxiliary momenta. So you augment your state space and your target distribution with these auxiliary momenta, and that in some way accelerates sampling. So today I'm planning to explain, because many of you won't be statistical physicists, Statistical Physics 101, the concept of broken symmetry, which I'm guessing most of you won't understand. Of course, people like Werner understand, Luke will understand. Then eventually Monte Carlo for smooth target distributions, before finally moving on to breaking symmetry on the auxiliary momentum space. So I'm going to bore you with a bit of notation because I'm a physicist, so that we all know what we're talking about. So if you see some bold script R, that denotes the what you would probably consider to be the parameter of your target distribution, but this is the collection of the positions of n particles, each on a d-dimensional space. So R1 is the position of particle 1, etc., etc. And so for some particle I, Ri might have x, y, z, etc. components if it's on a three-dimensional space. Pi is our target distribution. It's the Boltzmann distribution proportional to e to minus b to u. We use the potential. You've all seen this sort of stuff before. Important thing in statistical physics is that this potential u, which isn't necessarily the structure that you always see outside of statistical physics, is typically a sum over pairwise particle interactions. So for all the particles n, you have the two particle interactions, and this gives you your total potential energy. Beta is the inverse temperature. Theta is a vector of additional hyperparameters. This might be the volume, the mean density, etc. And then expectations are taken over R, and then the beta, theta, n are just constant hyperparameters, which we set, and then we study these expectations as functions of the hyperparameters, typically. So what do these positions R correspond to? So you've probably all seen, many of you would have seen the 2D Ising model. It's like the standard prototypical model that's presented to you when people are talking about statistical physics and phase transitions. Yeah? So in that case, each particle position Ri is just a plus minus one value, and you have these particles fixed on these sites of a periodic array. So they're not moving around, they're just exploring values in this spin space. So the positions then correspond to values in spin space. But you might have a collection of particles on some compact manifold, which is a subset of Euclidean space, in this typically a subset of Euclidean space, and then they typically have toroidal geometry. So here we have a collection of what we call hard disks on a subset of two-dimensional Euclidean space, and there's toroidal geometry so that this disk is this one, blah, 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 blah. Then you get more structured models. So you might, which Werner mentioned a couple of times towards the end of his talk yesterday, with problems in physical chemistry, where you have You'll typically be on a 3-dimensional torus, and then you might have some long chain molecule where each of the particle positions now corresponds to one of these particles, and then each of the 2 particle interactions might have some spring potential, a bit like in the model that Werner presented, to give you to define some molecule in some sense, but then you might also have intermolecular interactions between particles that are not part of the same molecule. And this gives you much more complex models, like you might have a polymer in a water solvent, for example. Is that relatively clear? We're all good? Good. We typically have periodic boundaries, so I think you're all comfortable with this. So yesterday, I'm really sorry, I've forgotten your name. Who works at École de Pont? What's your name again? I've forgotten your name. Gabriel. Yeah, so Gabriel was talking about models of the torus. So there you obviously have periodic boundaries. But in addition, these lattice models, they'll also have periodic boundaries. So these spins will be neighbours with these spins, etc., etc., etc. Do this because we're trying to recreate windows within small windows within large macroscopic systems, and we want to get rid of boundary effects, and also for convenience and things like this. So one thing that's quite strange in statistical physics from a Bayesian perspective is that our models typically have no input data. This might seem a bit crazy because I thought physicists were supposed to be modelling experimental measurements, so why do we not have any input data? It's because in statistical physics what we're typically interested in is taking some model for microscopic particle-particle interactions and using statistical frameworks to make macroscopic predictions based on the collective behaviour of large numbers of particles. And that's what we're typically doing. So we're more interested in the emergence of collective behaviour rather than modelling some input data, although sometimes this is the case. So we're typically interested in how the behaviour changes with some parameters such as the inverse temperature beta or some other hyperparameter. And then this is often characterised by the thermodynamic limit of some expectation changing form across what we call a phase transition. So the thermodynamic limit is just the infinite particle limit. And so, for example, you might have a magnetic material that at high temperature is non-magnetic and then at low temperature is magnetic. And so some well-chosen expectation value would be 0 at high temperature, non-zero at low temperature. And so you get this, and in the thermodynamic limit, this thing changes form across the phase transition. You tend to get and then you get non-analytic behavior at some phase transition. Okay? Good. Okay, so, well, first of all, I don't need to actually, I'm going to say, apologies to people from Bristol who saw a similar talk a couple of weeks ago. This is where the talk starts to change a little bit. Although then it will step back towards. So, any non-physicists in the room familiar with the concept of broken symmetry in physics? That's quite good, because then we've got something to talk about. What about the physicists? Good.
Well, familiar.
Werner's not got a clue what he's talking about. Okay, so when we don't know what's going on in physics, especially at a continuous phase transition, we turn to the 2D Ising model, which I just mentioned before. So it's our dependable friend, the 2D Ising model. As I said, we've got this array of particles fixed at the sites. We've got a set of particles fixed at the sites of this square array with toroidal topology, periodic array, governed by this interaction potential. So these RIRJs are the spin values, which are plus minus 1. This sum over this strange notation just means the sum over nearest neighbours. So I'm sure quite a lot of you are familiar with the Ising model. You all okay? Good. So what we're going to do to understand broken symmetry, like the most basic exposition of it, we're going to map this large n-spin system to a 1D magnetisation function. So in statistical physics, we typically have large numbers of particles, and we need to map, more broadly, we want to map information about the system onto some lower dimensional function. So when you have a magnetic system, the obvious thing to map it to is the magnetisation. So this is just the mean value of the spin. Okay, so when you're at high temperature, all the spins are pointing in different directions, and the magnetisation will typically be 0. So you get this. Oh God, got the wrong thing. So you get this this is the potential function for the magnetisation. Then at high temperature, the typical value will typically be m equals 0, and you get fluctuations around this, which is what we're seeing here. Then at low temperature, because the model is, go go back. It is symmetric with respect to global flips of all the spins. So if you take some configuration and flip all the spins, you have the same potential. This is the symmetry of the model. When you're at low temperature, the spins will tend to align, and as you cool, the spins will tend to align, and they'll either, the two most typical values are this is plus m0 and minus m0, and then you get small fluctuations around this. And you can think of this as this well corresponding to the bar magnet pointing in this direction, and this well corresponding to the bar magnet pointing in this direction. And this is actually, so a bar magnet is actually a very good example of broken symmetry. So the point is that when you call the model, or a magnetic system through the transition, it spontaneously chooses magnetization pointing in either the plus or the minus direction. And then the time scale on which that magnetization flips diverges with particle number. So this is what we call asymptotically slow mixing between states of equal probability density. And this is broken symmetry. So you can think of it as the probability of the magnetization flipping, changing sign, going to 0 in the thermodynamic limit. And this is dependent upon the dynamics you choose. So under metropolis dynamics, this is something that you observe. Okay? Okay, and this is sort of summing it up. So under metropolis dynamics, you get nice fluctuations around m equals 0, and you get symmetric mixing around m equals 0. But under metropolis dynamics at low temperature, you'll choose one well, you'll spontaneously choose one of the two wells. You'll look like you're mixing nicely, but just around that well. But the time scale on which you reach the other well will diverge with system size. So this is what oh my God, your name's gone again. Gabrielle was referring to as metastability. So you might have something that looks stable, looks like it's mixing well, but it's actually just mixing well around one mode. I'm sure you're all comfortable with the concept of multimodality, etc. Okay, so that was Statistical Physics 101, broken symmetry. I'm going to talk about event chain Monte Carlo for smooth target potentials. How many people have seen lots of talks about event chain Monte Carlo, PDMPs? Never. Legend. Okay, so because some people won't have done, I'm going to start with the metropolis algorithm for some simple smooth two-particle potential, and then build up to the event chain Monte Carlo from there. So we have some smooth two-particle potential U of R, so we just have two particles in our system. One of them is somewhere, we don't care where it is. This is the one that is currently what we call active, and it's starting at some position 0 in light orange here. So we choose some particle at random, we randomly perturb it, and then so this is the candidate position. We compute the potential difference, I'm sure you're all comfortable with all this, and accept the candidate with probability minimum of 1 exp minus beta delta u. So this is equivalent to accepting the candidate configuration if the potential difference is negative, but in this case the potential difference is positive, and so we accept it if some random number between 0 and 1 is less than e to the minus beta delta delta u. I'm sure you're all very comfortable with this. One thing that's slightly special in physics is that we almost always, that's correct, use single particle dynamics. So we'll randomly perturb a single particle at each iteration of the algorithm. I've been discussing actually with Sebastiano Grazzi a little bit before he left Warwick, trying to understand why we do this in physics. And we've been supposing it's because our models have translational symmetry, which is what gives us the freedom to break symmetry when we're looking at PDMPs. So I don't know if there's any connections. We could maybe discuss connections with what you were talking about yesterday with Gibbs, because you could view metropolis, what physicists call metropolis, as metropolis within Gibbs. So there may be some connections. But when you have translational symmetry, if you move two particles at once, you're almost wasting time, because translational symmetry means that the target distribution is a function of the separation vectors.
You make it too big a move.
Yeah, exactly. In some sense, yeah, exactly.
You can move 5 particles, but then you don't go
Yeah,
anywhere.
yeah, exactly, because the moves cancel out in some sense, so you're wasting time. So anyway, event chain Monte Carlo inverts metropolis, essentially. Can be viewed as an inversion of metropolis. So rather than making some random move and drawing a random number to decide whether you accept the move, we draw the random number at the start and convert it into what we call uphill energy. I'm sure you're all quite comfortable with this, but this is just reframed in a context that's comfortable for a physicist. So some random uphill energy minus log gamma. typically that should actually be divided by beta, it doesn't matter. We then perform a sequence of infinitesimally short metropolis moves until the first point at which a metropolis rejection would have occurred. So we're in the same initial position here, we've drawn our random number, we've converted it into uphill energy. We then make a sequence of infinitesimally small moves moving up the potential. This is using up our uphill energy. We then move downhill for free because metropolis moves are free when you go downhill. So this brown line is flat, and then we start moving uphill again until we've used up all the uphill energy. And this tells us how far the total displacement eta that we can move through in the original state space. And then there are some other moves that happen at these events once we've moved through eta that ensure correctness. And this results in continuous deterministic dynamics without rejections. And working out this eta corresponds to this equation essentially. So event chain Monte Carlo and PDMPs, in some sense more generally, become a problem in inverting this equation and finding eta. So let's sort of see where this equation comes from and how to sample eta. So this is hopefully probably maybe more useful for the physicists in the room. Okay, so we motivated event chain Monte Carlo as performing a sequence of infinitesimally small metropolis moves. So let's perform a sequence of small but finite metropolis moves in some fixed direction. So we're going to consider m metropolis moves of translations of length delta x in the positive direction, and then work out the probability of translating the active particle through the total distance eta equals m delta x. So the probability of translating, that probability is just equal to the product of the metropolis transition probabilities. I'm sure you can all do this maths to rearrange to have an exponential of some sum over the moves. And then in the continuous time limit, so in the limit that delta x goes to 0 with eta, the total distance fixed, we recover this slightly, I suppose, famous equation in the PDMP world, which is the integral of what we call the event rate. So max 0 and the derivative of the potential along the direction of motion. So ECMC essentially inverts metropolis in the continuous time limit. We get this probability of translating the active particle A through some distance eta. It's given by this. Blah, blah, blah. So this then corresponds to event chain Monte Carlo advancing some active particle at some constant velocity v from some time t0 and solving this equation. So solving minus log random number and solving it for t of eta to find the next event time. And this is assuming no what we call boundary collisions. We don't need to worry about that. Blah, blah, blah. And then particle I then becomes active with probability proportional to max 0, blah, blah, blah. And this sort of balances flows in some sense or whatever. Okay? All good? It's loose, but we're doing physics, so it's fine. Okay, so this amounts to sampling a non-homogeneous Poisson. This amounts to a non-homogeneous Poisson process for the next event time t eta. So for people the few physicists in the room, not Werner, but because he knows all about non-homogeneous Poisson processes, but you can think of this as queuing theory with a variable rate Q. So in a homogeneous Poisson process, this event rate would just be independent of the system state, and then you just get some standard queuing theory. So you can think of this as some blah, blah, blah. But the problem is, as indicated by this emoji, it's just telling you how to feel. Sampling from a non-homogeneous Poisson process is typically quite hard. And this is because we need to integrate this function, v dot grad of u, over only the positive contributions. So if you have a two-particle system, this is typically not too difficult because you can work out if you're going downhill or uphill, and you can work out where the next valley and top of the hill is. But as soon as you have multiple components in your potential u, which is what happens when you have multiple particles, then it becomes very challenging to work out these things. People following?
Is that true only in some density? If they don't really see each other, like n greater than 2 is just like a
Yeah, so I suppose you could argue that this is only true for truly long-range interactions in some sense. If you have a piecewise constant model, which is like the hard disk model, for example, then these things are much easier. And if you have, but typically, even if you have short-range interactions, you still have this issue because you can never guarantee that the third particle is not going to be nearby. Okay, but we have multiple options to proceed. One is thinning the Poisson process, which I'm sure many of you are familiar with. Familiar with lots of this. superposing two particle Poisson processes, so superposition of independent, so you can sample from each two particle interaction, and these are then independent Poisson processes. If you then take the soonest event time of each of these independent Poisson processes, then that is a sample of the event time of the summed or target Poisson process. And then another option is the notion of exact subsampling, which quite a lot of people at Warwick have been working on. Werner designed a subsampling scheme for in statistical physics, and it's very useful when you have long-range interactions. When you don't have long-range interactions, the two main strategies are thinning the Poisson process, so you choose some simple lambda hat that overestimates your target event rate, and this is something that will be tractable, so something whose next event time you can sample, and then you confirm events with probability given by the ratio of the target event rate in this overestimated one. Superposition of Poisson processes, I'm sure you understand. Okay? Good. PDMP has actually solved a problem in physics, an applied problem. So I don't know if that's actually the case in Bayesian inference. So what's wrong with that? So the first model to which it was model for which it was developed was the two-dimensional hard disk model, which Werner did with Etienne Bernard back in 2011, and they applied it to solve the 2D melting transition. So this was actually the physics question that was, in some sense, attempted to be answered by Metropolis et al. And then Alder and Wainwright. But their simulation methods converged far too slowly near the melting transition. I've got time to explain it. But Werner and Etienne's work managed to converge on much more reasonable timescales, and they were able to resolve the mechanics of the transition when you have a system of when you have a planar system transitioning from a solid to a liquid. And they actually found that it did not agree with the theoretical predictions. It was actually subtly different. And it then led to some beautiful hard disk experiments by my collaborator, well, soon to be collaborator, hopefully, Alice Thorney work at Oxford, where she confirmed these ECMC numerics. So this was a really exciting and beautiful period of statistical physics in the 2010s.
Can you explain a bit more what I see on the left-hand side of that picture?
Okay.
I'm a physicist.
You are a physicist?
No, definitely not.
Okay.
Otherwise, I would probably understand what I am.
The significance, well, I went through it very quickly. The significance of this picture is that you have what we call phase separation. So you have a large system here of hard disks. We haven't explained what hard disks are, but they're basically piecewise. It's a piecewise constant target potential, but you just have disks. They can't overlap, and then if they don't overlap, then the probability density is constant. As you increase the density towards the solid phase, you start to see configurations like this. And in this blue area, you can think of this as liquid phase, and this non-blue area, you can think of it as solid phase. I can't remember which around the colouring was. But when you see configurations like this, where you have what we call phase separation, so you have large areas that look like one phase and large areas that look like another, that indicates what we call a first-order phase transition rather than a continuous phase transition. And so the theoretical predictions were that this was supposed to be a continuous phase transition, but their work found that it was first-order, so it was quite a significant finding. Does that answer your question? In some sense. This isn't enough to say that it's a first-order phase transition, it's just a significant indicator. You then have to do work computing the free energy as a function of the density. And then you can start to show more rigorously that it's a first-order phase transition. Okay? So I'm now going to talk about breaking symmetry on the augmented, on the auxiliary velocity or momentum space. I'm going to switch between velocity and momentum because, I don't know, I just will. Because the masses are constant, it's the same thing from a physicist's perspective. Is everyone happy so far? Yeah? Okay, so it's a good point to start with in some sense. So why does what we just presented work? So slightly more rigorously, I suppose. So what we've done is we've augmented the state space, as I mentioned a few times. We've augmented the state space. So original state space is the particle positions are. We've augmented it with by assigning a momentum or a velocity to each particle. Our original target distribution has then been is replaced with this augmented distribution mu, which is the product of the original distribution and then a distribution for the velocities. So nu of v is some symmetric distribution for the velocities v r dn. Convergence on pi is then ensured by mu invariance, which Christoph and Sam did, yeah, by that mu q self-adjoint stuff, and then irreducibility, which more recently for a couple of models, Manon and some other collaborators did, and then obviously aperiodicity. Okay, but what we're going to talk about today is how so for these things to be correctness of these processes has only been shown for the distribution for the velocities or the momenta being symmetric. What we're going to do is we're going to break symmetry and momentum space. So there's no proof for this being absolutely correct, but numerical results agree. So it's an important point is that the important point is that when we're breaking symmetry and momentum space, we're taking advantage of some of the structure that's unique to us models in statistical physics, which I'll explain in a bit more detail as we go along. Essentially amounting to the toroidal topology and also the translational symmetry that you see in these models. So a nice exposition of this is the 2D XY magnetic spin model. So we're going to talk about metropolis simulations of this model and then also event chain simulations with broken symmetry. So I'm guessing most people have not seen this model before. You've seen this model before? You've seen this model before? Okay. Sam's seen this model before. So it's a bit like the Ising model, but it's like a more sophisticated model magnet. So we again have a set of spins fixed at the sites of this periodic square lattice, but instead of the spin values being plus or minus 1, they're now two-dimensional vectors of fixed length. So they're parameterized by their angle between minus pi and pi. The interaction potential is then just minus the sum over the nearest neighbours of the cosines of those nearest of the phase differences. So this encourages all the spins to point in the same direction, but then at high temperature they all point in different directions. This is a very important model in statistical physics because it admits what's called the Berezinski-Kosterlitz-Thouless phase transition. This was the first what's called a topological phase transition. It led to lots of activity, 60s, 70s, 80s, and even to today. And it led to the 2016 Nobel Prize in Physics. So it's the start of topological phases and phase transitions in statistical physics. So it's a really important and interesting model. Lots of structure to it that you don't get in other models. Metropolis simulations of this model, it's quite straightforward. You have some, did I do another thing? Yeah. Don't know what I've gone. It's probably a bit too obvious, but you have some discrete spin rotation via some Gaussian or uniform noise. Again, we choose some spin at random. We're using these single particle dynamics I mentioned before. Some innovation noise from some Gaussian uniform distribution, and then accept to reject step is based on the total potential difference due to all four neighbours, because remember we just have a nearest neighbour interactions. So event chain simulations, rather than doing this, they instead continuously advance some active spin, so a single spin again, in some fixed direction. So here it's advancing in the anti-clockwise direction. And this, because we have these nearest neighbour interactions between each of these four spins, it becomes a real challenge to sample the next event time if we consider the original target process. So we instead perform two-particle superposition. So we draw one event time for each of those two-particle interactions. And then the soonest of these event times defines the next event and vetoes the motion in some sense. And this vetoing spin then takes over with probability 1 and with the same momentum, which might seem a bit strange. This is the bit that should seem a bit strange. Okay? Any questions? Anyone notice anything strange? Go on.
With the velocities, symmetric distribution.
Yeah, exactly. That's the point. Yeah. So this is.
It doesn't have to be max value.
No. It just has to be symmetric. Yeah. No, it doesn't have to be. So they're very much artificial momenta. It's just auxiliary momenta that have been introduced to improve sampling. Essentially. And then in theory they should be symmetric, but in this problem, we've just noticed the key thing is that the vetoing spin takes over with probability 1 with the same momentum. So the symmetry has been broken on momentum space, which probably seems quite strange. I don't know. And this works thanks to the translational symmetry. So do you remember so in this case, the translational symmetry corresponds to the target distribution is a function of the differences of the states, the differences of the positions of the particles. And this is a common feature of statistical physics models. And so when this happens, if you move some particle, then move the other particle the same amount, then you're in the same position as you were before, same situation as you were before if you have a two-particle model. And in addition, our models have a toroidal topology. So in this case, the toroidal topology that's important is the fact that if you rotate the spin all the way around, you're back to where you started. So these two features mean that you can, at least intuitively, break symmetry on momentum space. But the point is that there's no proof. So we have proofs for mu invariance of these processes. We don't not have proofs for irreducibility. So this is sort of an open question, probably for ergodic theorists. But all numerical experiments suggest that these techniques work quite well. And it's something that we like. This can be very useful in physics because it can accelerate sampling in some important areas of thermodynamic phase space. So in low temperature phases when symmetry is broken, as I'm going to show here, and then also our hypothesis is that this will really help at phase transitions as well. Okay, so we can to help to sort of maybe make this seem like a slightly more mathematical grounding, we can consider a sort of skew detail balance in some sense. So if we just have a two-spin model, so we've just got two spins interacting with each other, the probability, you can think of these dynamics as the probability of starting in this state, so just have some two parts, starting in this state, with this particle, the initially active one, moving with velocity +1, so v equals 1, 0, over some time period, such that it displaces by an amount delta. That's the same as the probability of starting in that state, and then the other particle being active, and then moving through that distance delta through the same time period. And then by translational invariance, those two states are the same because the target distribution is just a function of the separation vectors. So this can be thought of as some sort of skew detail balance. But as soon as you have multiple particles, this thing doesn't really work as an exposition of why this sort of works. Okay, but now back to the large N model, and so we can look at, so that was just a two-spin sort of exposition. Let's go back to the large N model and think about broken momentum symmetry. So we're going to map this. So before we mapped that Ising model to a one-dimensional magnetization function, we're now going to map this large N spin model to a 2D magnetization vector. So rather than being the sum over the spin, the mean value of the spins, we've now got a sum over this, the local spin vectors. So this is the x component of the spin vector, and this is the y component of the spin vector. It's just the cos of the angles, blah, 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 blah. So what are we expecting when we collapse the system onto this function? So this is the probability distribution of the norm of the magnetization vector for various temperatures. So this is at high temperature, T equals 4, doesn't matter what these numbers are. Low temperature, T equals 0.5, and then here the temperature is increasing, T equals 1, T equals blah, 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 through the transition. This spread out probability mass is something we're going to talk about later, and this is where Gareth and I have a shared student who's going to be looking at the power of these techniques in accelerating sampling when you have these challenges of broad regions of spread out probability mass. But what we're expecting is that at a low temperature where all the spins are pointing in different directions, you get a typical value, a typical magnetic norm equals 0 with fluctuations around it, and then at higher temperature you get sort of a ring. So you get something that looks so this is mx, my. You're going to expect something that looks a bit like this, but with some sort of fluctuations around it like that. Does that make sense? Yeah. And you'll also notice that we have this quite an interesting effect here. There's this is something I'll hopefully, if I have time to talk about it later. This looks a bit like some sort of Gaussian translated up to some positive value, but which is asymmetric towards m equals 0. And this asymmetry is obviously difficult to sample with diffusive sampling algorithms, and this is actually a consequence, in some sense, of the topological nature of the transition, consequence of something called the Mermin-Wagner theorem. But anyway, when you do metropolis simulations of this model, they mix asymptotically slowly around that ring. So asymptotically slowly around this ring. So they're mixing asymptotically slowly between states of equal probability density, and this is what we called symmetry breaking earlier on. So it's a slightly different type of symmetry breaking. So before we had two wells that were separated almost discretely, but here it's a continuous symmetry, so you can continuously move around this ring. I'll explain this in a bit more detail in a second. So this type of symmetry is slightly different, but we still get asymptotically slow mixing between states of equal probability density at low temperature. So what we're seeing here is 6 different simulations. This is of a 16 by 16 system, 2 different simulations. 2 different simulations at a larger system, and then 2 different simulations at this 256 by 256 system. All the black data, each set of black data is, in some sense, the trace plot of a simulation at low temperature, and the red data is the trace plot of some simulation at high temperature. All the simulation timescales are the same, scaled by the number of spins, the number of attempts. All of the high temperature ones in red, they're centered on m equals 0 as you'd expect, with fluctuations around them. The fluctuations get larger as you get to smaller system sizes, basically due to something called finite size effects. So basically, the exponential correlations, because the correlations decay exponentially with particle separation, the smaller the system size, the less disordered you are in some sense. But then at low temperature, these black trace plots exhibit what looks like symmetric mixing in the smaller system size, but then as you increase the system size, the mixing around the ring gets worse and worse. And this is what we call asymptotic slow mixing. And the mixing time is something that we can characterize if we have time, but probably don't. This is then circumvented by broken symmetry ECMC. So these are the same system sizes, temperatures, and as these plots, but with broken symmetry, eventually Monte Carlo. As expected, the high temperature simulations in red all mix very nicely, blah, 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 blah. But at low temperature, we get symmetric mixing on short timescales for all system sizes. So this asymptotically slow mixing, this broken symmetry on the original state space has been recovered by event chain Monte Carlo with broken symmetry on momentum space. An additional thing is that, you remember that heavy tail towards m equals 0 that I mentioned? You can see these small fluctuations towards m equals 0 for the metropolis simulations. You get much better mixing towards m equals 0 as well when you're doing this.
So these all take the same time to run?
Yeah, so they're all for the same time scaled by the number of particles, essentially. So you'll attempting n one time step in each of these metropolis simulations is attempting n particles.
You know, why is the size of the ring thickness not decreasing with n?
It does actually decrease with n, but it decreases with n very weakly. So it decreases with n. It's basically a consequence of the Mermin-Wagner theorem. So when you have a two-dimensional system with continuous symmetry, it's actually quite interesting. So the scaling, so the norm of this expected magnetization does actually go to 0 in the thermodynamic limit, but very, very slowly. At the same time, its variance is also going to 0 in the thermodynamic limit, very, very slowly, and with the same scaling. And so then the ratio of that the ratio of the two does not go to 0 in the thermodynamic limit. An interesting case. But yeah, so it is actually getting smaller, but
I think it's also because we want lines rather than dots.
yeah. So the other thing is, yeah. So a heat map would have been nice. I was trying to. It's difficult to find the ideal way to present all this in one place. But I do think the main reason is that it is going to 0. It is going to 0, but very, very slowly. Characterize the mixing times. So we could talk about how to characterize the mixing times, but it's a bit dry. And we haven't got loads of time, so I think I'll probably skip this. We were going to decide how to, because we started late, we were going to decide which slides to skip. using some homogeneous Poisson process. But instead, let's skip these ones because I haven't got loads of time. But basically, you can characterize these mixing times by analyzing the empirical cumulative distribution functions of the phase of the magnetization vector. And essentially, as this is smaller system size, larger system size, and this red data is at low temperature, you're expecting the empirical cumulative distribution to target the CDF of the uniform distribution, which is essentially this line in black. That's what you're seeing at high temperature. But at low temperature, there are large deviations away from that behavior, and that's because you haven't mixed rotationally on the timescale. And the effect gets worse and worse as the system size increases. And you get non-reproducible simulations, which is what you'd expect with broken symmetry. Blah, 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 blah. And then you measure it by the Kramer von Mies mean square distance between your empirical CDF and target CDF, which is a measure that you might be familiar with. This essentially characterizes how much discrepancy there is between your simulation and your target. A bit like the Kolmogorov-Smirnov test, but with a bit more information involved. Then you can do this thing, blah, 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 which essentially shows that the Kramer von Mies mean square distance multiplied by the number of samples is proportional to the mixing time, and then for metropolis simulations, which is these data in the circles, the mixing time scales with the number of spins at low temperature, but then it's system size independent at high temperature, and then the event chain data with the stars is weakly dependent on, is non-divergent with respect to the number of spins at all temperatures. So we get a mixing time that diverges, it's proportional to the number of spins, diverges with particle number for low temperature metropolis simulations, otherwise it's non-divergent. So low temperature, the metropolis simulations have this divergent mixing time, and then the symmetry broken ECMC has a tau mixing time which is non-divergent. So breaking symmetry on momentum space in event chain Monte Carlo has recovered symmetry on the original state space. Although you might then say, but you haven't done ECMC without breaking symmetry on momentum space. And that is true, but that's something that mine and Garrett's PhD student is going to look into over the next few years. Blah, 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 blah. Now this is really important. So all good physicists would say, who cares? Because usually when you're doing physics, certainly experiments, you're measuring the absolute value of the magnetization. You don't really care about its direction so much, essentially, in some sense, because it's symmetry broke. All states are symmetric. But the key point is that if we go back to these plots I showed you earlier of the probability density of the probability density of the norm of the magnetization vector. So this was at low temperature where we have which is reflective of the ring, high temperature reflective of the disorder. When you when you heat the system from low temperature, where you have this ring, to high temperature, where you have a unimodal distribution, you necessarily flatten the probability distribution at the transition. So you get this spread out region of, in some sense, flat probability mass. And this is obviously really hard to sample under metropolis dynamics. And then you get these very noisy estimated expectations of what we call the magnetic susceptibility under metropolis, for metropolis simulations. You also have this problem at low temperature as well, which is an effect of this tail here. And so the hypothesis is that breaking symmetry momentum space will fire us through these regions of flat probability mass around the transition and allow us to improve the predictive power of the predictive power of Monte Carlo sampling algorithms at this phase transition, also at phase transitions more broadly, because you will often get these spread out regions of probability mass. And so classical sampling algorithms tend to suffer these problems when you're applying them in the regions in which you actually care about, because you usually have designed these models to understand phase transitions rather than to understand the physics away from the phase transition. So these traditional sampling algorithms tend to work really well away from phase transitions, but you don't really care about that because experimental systems have non-leading order behavior away from the phase transition. But at phase transition, these models are very good representations of the physics, but this is exactly where classical sampling algorithms, traditional sampling algorithms tend to fail. So this is where PDMPs offer a lot of promise, certainly with broken momentum symmetry in statistical physics. Okay, so I've got 2 PhD students working on PDMPs to circumvent these strong one's working on PDMPs to circumvent these strong autocorrelations, so leading to those noisy statistics in this XY model, and then also another working on an analogous problem in what's called world-line sampling in computational quantum field theory, where you also observe these problems of strong autocorrelations due to something analogous to a phase transition. Okay, so summary, physicists often use sampling algorithms to study phase transitions, eventually Monte Carlo or PDMPs more generally, accelerate mixing especially, question mark, when momentum symmetry is broken. The question mark is because we need to do it without breaking symmetry as well, but it seems like a very strong hypothesis. I have a PhD student with Gareth working on broken symmetry PDMP dynamics for strong autocorrelations at phase transitions, and another working blah, blah, blah. I understood a lot of this working with Sam Livingston, and we wrote a beautiful interdisciplinary paper about sampling algorithms in statistical physics. So if you're interested, read it, and then whether or not you're interested, cite it. Thank you very much.
Okay, do we have questions for Michael?
Yes, having in mind the first talk of Werner Kraft, we have this parameter B that you can play with. And so here in the 2D XY model, you could write cos of phi as cos of phi plus B and sine of phi. So you can do the same kind of different way of writing your potential, and then you would have some. So particles would have some trend to be not equal but separated by a given phase. Do you think that it could help? Has it helped in the linear or harmonic chain?
I was wondering about this overnight. What was your proposition?
So like you write that instead of saying my energy is cos of phi I minus phi j,
yeah.
I say that my energy is cos of phi I minus phi j minus b. Then I have to remove from that some some sinus of.
Okay, then you remove the sign.
Yeah.
Yeah.
Okay, so you have something which is the same, but now if I do it.
I think the non-linearity would mean that you've changed the model, then, wouldn't it?
No. You don't change the model, and then.
Have you thought about it? I was actually going to ask you about this.
When you do the event chain, you treat separately both parts, as it was done in the harmonic case.
Yeah.
And so you don't have the same dynamics, and so possibly you have this same deterministic trend to turn.
I suppose it depends whether or not you can infer your factor field thing.
As you are saying, there are infinite possibilities.
It did work in your harmonic chain, so.
But when you with the harmonic chain, it didn't introduce any. It didn't change the potential because it just introduced a constant. It corresponded to adding a constant to the potential, didn't it?
But it was the same manipulation where you say either I have xi minus xj minus b square, or I have xy minus xg square minus b xy minus xg. It's basically exactly the same kind.
But then when you sum over the signs of the phase differences, because it's not going to sum. That's not going to sum to 0, is it? Because of the non-linearity.
I would be part of it.
Oh, you've done it. Okay. I wanted to discuss this with you at lunch, so maybe the three of us could discuss. So yeah, I mean, that sort of change to the potential is actually how you would model Josephson junction arrays. So you have an extra field A, ij between any two links. So these can be the phase of your condensate of the Josephson phase between superconducting qubits, blah 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 blah. So you can view this as some sort of augmented distribution in some sense, and then you can sample over that potentially. What were you going to say?
No, I just want to just make a comment that it's kind of very interesting that that's in these models, in the spin models, you see that these local methods can have different scaling approaches, so they scale differently with for infinite systems than the metropolis algorithm.
Yeah.
That was kind of very interesting to understand that the local algorithm, that not all local algorithms are the same. I have the the conjecture, and I think we have the conjecture that all local reversible algorithms are the same. So if you have theorems,
You mean the scaling is the same?
yes, are scaling the same. If you have theorems that prove the contrary, please come and discuss with me because I really need information on it. But here it was possible to show that local algorithms in this model could have much faster scaling. The problem is that there are much better algorithms than this one. So let's say there was decades. There have been decades. There have been half a century of discussion on the hard disk model. There have been decades of wrong papers on this model, and this was completely eliminated when the cluster algorithms were set up for these models, and the cluster algorithms for the XY model. And it's those models who are able to actually show that Costa-Solstead transition took place in that model. It's extremely difficult to fight a good cluster algorithm. But unfortunately or unfortunately, they work for these models. So ECMC will never be able to obtain any interesting physical results on these models. That's my opinion.
There's still some interesting
It's very
structure
interesting,
too.
very interesting.
It's a very interesting. There's still interesting structure to look into. Essentially, it becomes in a very interesting setting for understanding these processes sort of more broadly as well.
We just have one final question, and then I think we'll end.
I don't know if this now. So you're describing how you chose your velocity distribution that you're always going one way around the circle, and later on you're saying, well, normally people will get symmetric distributions. Why did you decide to do it this way rather than doing it symmetrically?
So, I mean, that's sort of an interesting question. So, I'd say that initially, when physicists were developing venture Monte Carlo, it was sort of, for some reason, it was the intuitive thing to do. It's the intuitive thing to do. Now the argument is that when you have this toroidal topology on either your spin space or your compact manifold, you're going to accept. Well, numerical results seem to suggest accelerated mixing compared to symmetric momentum sampling. And as I said at the start, so bouncy particle sampler and zigzag sampler in Bayesian computation, when you get to high dimensions, they tend to recover diffusive dynamics, whereas this will preserve the ballistic dynamics on longer timescales is the hypothesis. But this is something that Gareth and I want to understand in more detail with our PhD students.
So if you wanted to do if you wanted to make it symmetric, how would you change what it is that you described?
So when an event occurs, you'd have some probability of bouncing back with the same spin or some probability of the other spin taking over, rather than just assigning probability 1 to that new spin taking over and moving.
Okay, I think we'll have to leave it there. So let's thank Michael again.